So, we will continue our discussion about specific heat, which is which depend on the temperature, especially at lower temperature. So, how to explain? Dulong-Petit law could not explain. So, then Einstein came forward and he tried to calculate the specific heat for a solid, and he found that in this Dulong-Petit law there. So, what we have considered this in solid, this lattice are there, atoms are there. So, they behave like a harmonic oscillator. So, they oscillate, they vibrate, okay, and they are independent, they do not talk to each other, and they can take any value 0 to, they can take any value of energy 0 to infinity, they can take any value. Okay. So, but Einstein he considered the similar model, that the solid is made of atoms, lattice, and this each lattice point or atoms behave like a harmonic oscillator, okay. And he considered that they oscillate, they vibrate independently, they are not connected with the nearest neighbor. So, they can vibrate independently. Okay. So, and then only he considered that following the Planck's discovery, that was the turning point of, that is the beginning of the quantum mechanics, right. So, this Planck's considered when he was trying to explain this black body radiation, and he considered that oscillator, harmonic oscillator, it cannot take any value between 0 to infinity. So, it can have only discrete, it can take only discrete energy. So, and he tell that E equal to basically energy of the oscillator, it will be controlled by this relation n h nu, okay, or n h cross omega. Okay. So, harmonic oscillator, so they will oscillate with this same frequency, okay, and but they cannot take any energy, they can take only energy that is n equal to 0, 1, 2, 3. Okay. So, that means that systems, harmonic oscillator, that systems are in a are having these systems are having discrete energy level. So, one can tell this vibrational energy level, okay, they vibrate. So, they can take, so they are equally spaced, by h nu, okay. So, this is 0, 1, 1, 2, 3, 4, 5, okay. So, this oscillator can have only this value, not any other value, like in between they cannot. So, that is the additional criteria or assumption Einstein made over this Dulong-Petit law. Okay. Whatever Dulong-Petit considered the model, this he considered same model, but only they considered that energy can vary 0 to infinity, but here Einstein considered that energy varies like this. So, this discreteness. So, in 1900 this Planck in 1900, right, 1900 or 1901. So, this Planck constant, Planck Planck's distribution of energy. So, that is in that time. So, this was the for oscillator, harmonic oscillator, this was the suggestion came from the Planck's, and this was a great success to explain many things like this black body radiation, photoelectric effect, right. And then here also for specific heat. So, that concept was taken by Einstein and try to explain these thermal properties, this dependence, temperature dependence of specific heat, right. So, what happens? So, this was the classical model, right. Dulong-Petit used this one. Now, in case of when Einstein considered this energy, so what? So, average energy. So, average energy. So, this one can calculate the same way, but it was concept this energy distribution, that was that concept was this classical concept. Maxwell-Boltzmann statistics was used, and Einstein again he argued that this that oscillators are fixed in space. Oscillators are fixed in the space. Oscillators are fixed in the space, and with respect to this fixed position, they are oscillating. Okay. Now, they have location. They are sitting at a particular position. So, this oscillator can be identified. Each oscillator can be identified. So, they are distinguishable. Okay. Since they are distinguishable, so one can use classical statistics, Maxwell-Boltzmann statistics, and that is the difference. You see, classical and this quantum. In case of quantum statistics, there these particles are indistinguishable. Like in electrons, free electron theory, there we have considered Fermi-Dirac statistics, because there you cannot identify electrons. So, all electrons are similar. Here all oscillators also similar. Okay. One can apply the other quantum statistics because you may consider that they are oscillating identically there, so we cannot distinguish them. So, that was not considered by Einstein. Einstein argued that since they have location, they are located in a particular position, okay, with respect to that it is oscillating. So, we can identify each oscillator. So, they are distinguishable. So, classical statistics is applicable. Okay. So, that is why he considered the Maxwell-Boltzmann statistics, means this the distribution, this distribution was considered. But so, that means he used quantum oscillator, means energy cannot take any value. Okay. So, it will take discrete energy value. So, that is why it is quantum oscillator, but it follows the classical statistics. So, that is what the Einstein took into consideration. Okay. So, that means this saves this we can just replace, with this continuous integration, just we can replace with the summation. So, this E is basically is H n nu, H n H nu, and this will be n H nu. Okay. And here it will be n h nu, and this integration will be replaced by summation. So, summation this for n equal to 0 to infinity. Okay. So, that was considered. So, average energy one can find out from here, and he considered that this. So, n number of particles are there. Okay. So, they are oscillating. So, it has 3. So, in 3 dimension, means each particle will have 3 degrees of freedom. So, that in so he considered equivalent one dimensional oscillator. So, that number is 3 n. So, he considered 3 n number of one dimensional oscillator, okay. But solid is 3 dimensional. So, it can oscillate along this, it can oscillate along this, it can oscillate along this. So, we can bake it into 3 one dimensional oscillator. So, that is what he did. So, this whatever here we are getting energy of each for each one dimensional oscillator, So, this we have to evaluate now. So, how to do that? So, this you can do, just take I think what we can do. So, this we can write, So, n equal to 0 to infinity. So, for n equal to 0, so this will be, this term will be 0, right. For n equal to 1, I will get n equal to 1. So, h nu I can take out, and then I can write term 1 into e to the power minus h nu by k t kbt, right, plus 2 into e to the power minus h nu by kbt plus etc. So, infinite series, okay. Divide by here what I will get? I will get for n equal to 0, this is 1. So, I will get 1 plus e to the power minus h nu by kbt plus e to the power minus 2 h nu by kbt. Okay. So, if I replace h nu by kbt, so if I take x equal to minus h nu by kbt, so I can write this series as a h nu, then this e to the power x plus e to the 2 e to the power 2x. So, here it has to be 2 plus e plus 3 e to the power 3x divide by I can take 1 plus e to the power x plus e to the power 2x plus e to the power 3x, right. So, this in principle I can write like d by dx h nu I can keep here. So, this I can write d by dx log 1 plus e to the power x plus e to the power 2x. Okay. So, log x. So, if I differentiate, it will be 1 by x, right. It will be 1 by x, right. So, and d by dx of x, whatever inside is there, right. So, I will get this term 1 by x, 1 by this, 1 by log n. So, differentiate 1 by this. So, I will get this denominator, and then this dx will apply on this. So, I will get here it is e to the power x. So, it will remain e to the power x, then here e to the power 2 x it will be there, and then 2 x will give 2. So, 2 e to the power 2 x. So, I will get this term. So, this in principle I can write like this, this we can express this way, and this is a series, infinite series, and this will give you, just if you do it. So, this will give you 1 minus x, if x is. So, here I think we have to no, it is 1 minus e to the power x, it gives basically 1 by 1 minus e to the power x, right. So, that series will give this. Now, if you differentiate it with respect to x, so what we will get? So, this basically this again ln. So, this I can write this I can write this minus 1, right, minus 1. So, this if I differentiate, I think I can write this side. So, this average energy of each one dimensional oscillator. So, this I will get E equal to h nu, and then if I, so this ln, this minus 1 means minus 1 may come. So, minus 1, this minus 1 will come. So, ln of this one. So, what we will get 1 by x. So, 1 by this I will get 1 by this 1 by 1 minus e x, and then if I differentiate this part. So, it will give minus e to the power x, it will give minus e to the power x minus e to the power x, right. So, this term is like this. So, it is minus minus plus h nu e to the power x, e to the power x. So, this equivalently I can write 1 by e to the power x if I take down. So, it will give me 1 minus x minus 1, right. Okay. So, this my energy, this is the energy of one dimensional oscillator, average energy of one dimensional oscillator. Now, I have to find out total energy. So, total energy E will be, so multiplied by 3 n, right, 3 n number of one dimensional. So, E will be to 3 n. So, now C V will be d E by dt at constant V, it is there all the time. So, this now I can write in terms of x, I can take out and put here. So, that is the x, here it was minus. So, that is minus minus plus. So, it will be plus. So, e to the power h nu by k b t s, right. So, t is there here. So, I have to differentiate it. So, what I will get? I will get 3 n h nu, that is there, and here I have to differentiate. So, this part I have to put under the d by dt. So, T is there. So, this like 1 by x, right, it is 1 by whatever this function of t, right. So, if you differentiate it, so it is always a minus 1 by x square kind of things. So, this will give me minus 1 by, so minus will come here. So, e to the power h nu by kBt minus 1 whole square and 1 minus sign is there. So, this I can put here anyway. So, I will put now this part is done 1 by x square. Now, this part differentiate with respect to t dt. So, it will give me e to the power h nu by kBt okay. And then this part. So, again here 1 by t is there. So, it will give me h nu by kb and then minus 1 by t square, right. So, if you just differentiate, so this you will get, if you differentiate this will get. So, ultimately what I am getting, so minus it will go. So, I am getting 3 n h nu square okay, by kb right, t square and then I am getting e to the power h nu by kBt, this one divided by h nu by kBt minus 1 whole square. So, this will be the, so I do not need this part. So, I can okay. So, this will be the CV, this will be the CV. So, this I can write, this I can write here, I can multiply with 1 kb, So, this will be kb square and if I multiply with 1 kb okay. So, n kb it is r. So, I can write basically this will be 3r and then h nu by kBt whole square, right, and then e to the power h nu by kBt divided by e to the power h nu by kBt minus 1 whole square. Okay. Now, if I take two part, one is for low temperature and this is for high temperature. So, case 1, if you take case 1 this at high temperature, So, basically in physics, in science there is no things like high temperature, low temperature, always you need some reference. So, low temperature means below of what temperature, I will call it low temperature, below of what temperature, above of what temperature, I will tell this high temperature. Okay. So, we need always reference, otherwise there is no meaning of high temperature and low temperature. So, that one can define. So, if I define here, so h nu by kb, so that is the temperature. So, this that k, that T okay, equal to h nu, kT equal to h nu. Okay. Okay. So, if I this is the temperature is such a temperature, if I define by theta E Einstein temperature kT. So, k theta E equal to will be equal to h nu. Okay. So, then this theta E is my reference temperature h nu by k. So, this is called Einstein temperature. So, the temperature below. So, temperature here at high temperature means temperature is greater than theta E. Okay. So, then we will tell it is high temperature. So, theta is defined by like this. Okay. So, then here I can write here this one theta E by T square. Here I can write this one theta E by T, theta E by T. Here also I can define theta E by T. Now, when theta is very greater than theta E, theta is very greater than theta E, sorry, T is very greater than theta E, then T is very greater than theta E, right. So, this term is very small, theta E by T will be very small. Okay. So, it is like e to the power x or say some parameter e to the power say theta, e to the power y you take, y equal to theta E by a. So, y is very small. Okay. So, then we can expand it 1 plus x, it is basically 1 plus x square etcetera. So, I can neglect higher term, right. I can neglect higher term, this minus 1. So, it is basically x, it will give basically x, right. So, this term, so this for lower temperature C B equal to 3R theta E by T square, right, and here it is giving me sorry, I have written y. So, I should write y. So, y square, okay, below y square means theta E by T square. So, I am getting 1 by theta E by T whole square, right. So, these two will go and this term is there. So, this again e to the power x. So, 1 plus. So, this approximately this one can take 1 because 1 plus y plus y square etcetera. So, since theta is, if theta is very greater than theta E, so one can write this term is like 1. Okay. So, basically you are getting it is 1. So, this will give you equal to 3R. Okay. If theta is very greater than theta E, so I will get C B equal to 3R. So, that is nothing but Dulong-Pettit law. So, at high temperature, so we are getting the result as same result as the result of Dulong-Pettit, right. So, second you can think of that, so this also I do not need. So, this was the expression C V equal to this, right. So, now for case 2 for low temperature, at low temperature. So, low temperature means theta T is very less than theta E, right. Now, C V will be equal to 3R. Now, we cannot neglect this term is now higher. So, theta E by T square. Now, this theta E by T, that is greater than 1, it is higher term, right. So, it is compared to 1, it is higher, right. So, I can neglect 1. So, it will be square of this and then this one is there. So, it will be 1 by this. So, I can get e to the power minus theta e by t. I can get e to the power minus theta e by t, right, for this lower temperature. Okay, at lower temperature this. So, here what I am seeing, this theta e by t is very very high term, is higher term, right, because this theta t is smaller. So, this is higher. So, at very very low temperature, when temperature will be very towards temperature tends to 0. So, this term, this exponential term will dominate, right, than this term, because t is very very small. So, here in general it's CV is proportional to e to the power minus theta e by t square, right, theta e by t exponential term and this t square, right. Now, for very low temperature, so this term exponential term will dominate, because if this e to the power minus x, if x is very high, so it will fall very sharply, So, here CV curve, if temperature T, so this CV curve, as I experimentally whatever we have observed, this is the experimental, okay, this is the 3R, that is fine. So, this is the theta e, say this is the theta e, okay. One can find out theta e. So, this is the theta e. So, below theta e, so this below theta it is falling like this. Now, at very very low temperature, this falls exponentially, right, because this term is very very small. So, that means when you are increasing temperature, it is increasing like this. So, this so Einstein, whatever the result got, it can explain the behavior of lower temperature, but it is not fully satisfied, because its value was slightly, this if it is the experimental result. So, Einstein's result was slightly higher of that one, like this. Okay. So, this result it's could not fit with the experimental data completely. So, but partially it is successful. So, actually this curve, experimental curve, it can be fitted with the T cube law, this is called T cube law. So, it varies like this T cube curve. So, CV is proportional to this T cube. If so, then this fit the experimental curve. So, but this here it is the T cube, its exponential term is dominating. So, in case of Einstein, this at lower temperature, this it follows the exponential curve, okay, but experimental curve demands the T cube curve, okay. It falls following the T cube. So, then this Einstein model is not fully successful to explain the CV as a function of temperature, especially at lower temperature. So, then Debye came forward to explain this CV behavior at lower temperature, and he found the T cube dependent of the CV. So, that we will discuss in next class. Okay. So, I will stop here. Thank you for your attention.